Hello students, today we're going to talk about inscribed angles. Please make sure you take notes. So let's go ahead and get started. The first one here, we want to talk about a couple definitions so we know what we're talking about when we're doing this. The first thing is what an inscribed angle is. So we did central angles before, and those are the ones whose the vertex was sitting on the center. For this, the inscribed angle is the vertex is actually on the circle, and the sides are the chords of the circle. And then what we have is, with the two endpoints of those angles also on the circle, we have an intercepted arc. And that's the arc that is between and in the interior of an inscribed angle. So let's look at a visual of this. As you can see here, the inscribed angle is this piece down here. Okay, the measure of this is found right in here. It's touching the circle, and it has endpoints here and here. So now it doesn't matter that it has rays that are continuing off forever. The intercepted arc is going on right in between those two. So just to do an example here, all I want to do is determine whether these are inscribed or they are circumscribed to make sure we understand the difference. So let's take a look at the very first one. So what I see here is that we have two chords sitting on the inside, here and here, and its angle is on the inside. So based upon that, it's an inscribed. So looking at the next one, we have two that are on the outside of the circle, and the angle is found on the outside of it. So therefore we have circumscribed. So you see how that angle is on the outside of the circle and the two pieces connecting to it are on the outside. So looking at the other two, the same is going to follow. These are outside, the angle is on the outside, so that is also circumscribed, while this is on the inside. Moving on, we can find the measure of inscribed angles, and it's related directly to the arc that it's intercepting. And specifically, if the angle is inscribed in a circle, then its measure is going to be half of the intercepted arc, not equal like the central angle was. So taking a look at what we have here, I have this inscribed angle right here, angle ADB, and here is its arc, AB, that it's intercepting. So I can find the measure of that. Now remember, that's different than, say, what a central angle is, which is the measurement of that arc. Those two pieces are the equal pieces. To find the measure of angle ADB, we're actually going to cut it in half, because it's a little bit further back than angle C is. So to find that measurement, we're going to cut it in half. Now, if I were to give you the angle, you're then going to double it to get the arc. So make sure you know which one you're going towards. The arc is going to be bigger than the angle. So let's do a couple of examples of that. So let's find the measure of the blue arc or angle. So in this one here, I want the measure of this arc right here, STQ. So what I see is that it is an intercepted arc, and it's intercepted by this angle SRQ. And I notice that the angle is 90 degrees. So what that's telling me, if I set that up, is that QTS is going to be double that amount, because the arc is going to be double the angle. So then in letter B, when I go to find the angle here, now it's different. It's going to go the other way around. This measurement is going to be half of the intercepted arc that's found right there. So what I'm going to do to find that angle is cut it in half, so that one will be 40 degrees. So again, the angle is always going to be smaller than its intercepted arc. Moving on, we have the congruent inscribed angles theorem. And what that says here is if we have two angles that are intercepting the same exact arc, then those two angles are going to have to be congruent. So if you thought about it, if I gave you this arc here, this arc AB, I said that was, say, 60 degrees. If I went to find angle C, I'm going to cut that in half based upon the last thing I was just doing, so that would be 30. But what also happens to find angle D, I would do the same exact thing. So as long as they're intercepting the same exact arc, then the two angles are going to be congruent. So now let's apply this to an example. In here, I'm telling you that the measure of angle E is 75 degrees. What I want to do is find the measure of angle F. Well, we know that since angle E and angle F are both intercepting this arc DH right here, we know that those two angles are going to have to be congruent. And because they're congruent, that means the measures are going to have to be equal, so angle F is going to have to be 75 degrees. Okay. Let's move on. We're going to talk about a couple more definitions. We have ourselves an inscribed polygon. So now think back to when I was looking at inscribed versus circumscribed. Inscribed was always inside of our circle. So an inscribed polygon is a polygon whose vertices all lie on a circle. So it's going to be on the inside. Circumscribed circle is that circle that has an inscribed polygon. So let's take a look at a visual for this. Okay, the polygon itself is considered an inscribed polygon, while the circle is a circumscribed polygon because it's going along the outside. Okay, so when I reference circumscribed circle, I'm talking about the circle that's going along on the outside. The next theorem we have is about right triangles. If a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. Conversely, if one side of an inscribed triangle is the diameter of the circle, then the triangle is a right triangle, and the angle opposite the diameter is a right angle. Now think about what we were just doing with the inscribed angles. We always said it was half the arc. So if this is intercepting a semicircle right here, then it only makes sense that this is going to have to be a right angle. And the opposite is going to be true. If I were to draw a triangle in here and this diameter exists, it's going to have to be a hypotenuse because, again, it's also representing that intercepted arc there. Excuse me. So angle B is a right angle if and only if segment AC is the diameter of the circle. Okay. Moving on, about quadrilaterals now. Quadrilaterals can be inscribed in a circle if and only if the opposite angles are supplementary. So now think back to, say, parallelograms and stuff. We always said the angles next to each other are going to be supplementary. This is the opposite. Okay, instead of having them be next to each other, we want it so that they're across from each other. So that means angle D and angle F are going to be congruent or supplementary, and angle E and angle G are going to be supplementary. So those are what's going to add up to 180 opposed to the other way around. Okay, we want to find the value of each of these variables. So let's apply the properties that we just discussed. So in this one here, I can see that I have a diameter. So what that's telling me is that this triangle that's formed is a right triangle. So what I can say is that this is equal to 90 degrees, so I can set 2x equal to the 90 degrees. Well, dividing both sides by 2, I see x is equal to 45. So now for the next one, I can solve for y or I can solve for z first. It's not going to make a difference. Let's go ahead and solve for z. I know that opposite angles are supplementary, so angle M or angle D and angle F, they're going to add up to 180. So substituting in our values, angle F is 80 degrees. Subtract that from both sides, so the measure of angle Z, is 100 degrees. Repeating the exact same process now with G and E. We're going to set those two equal to 180 because, again, they're opposite from each other, so they are supplementary. And that means y plus 120 is equal to 180, so when I subtract, I get y is equal to 60. Okay, let's move on to our next example here. So the answer to this question is true or false. So what we want to do is take a look at our diagram here. I see I have a bunch of right angles in here, so I theoretically have 3 right triangles in there. I can also see I have some quadrilaterals if I were to focus maybe in on a couple pieces here. So let's take a look at the different examples. So the first one says angle P, so this angle right here, and angle Q intercept the same arc. Well, if I look at it, angle P is made up of TPR, so that's that first angle. So that's intercepting arc TSR. The second angle here is TQR, so this one here. So going end to end, I see I'm also intercepting the same arc. So the answer to this is true. My next piece to this is going to be if SRP and angle SRP and angle Q, if they intercept the same arc. So I'm going to do that same exact process. So I have SRP, which is this angle down here, and it's intercepting this arc PTS. So now I'm going to repeat that same process with angle Q, but once again, we saw with angle Q, it's intercepting this piece here. So the correct answer to that is false. The next thing is asking if TSR is a semicircle. So I'm looking here, TS to R, and what I can see is from T to R, it is a diameter because it's going through the center here at O. So the correct answer to that is true. My next question is angle PTS and angle SRQ, if they are opposite angles. So I have angle PTS, which is this angle here, and then angle SRQ, so SRQ. They are, in fact, not opposite angles. While they might be on opposite sides of this, we need to have it so that they share that point right there that they don't share. So since angles P and Q are not connected, the correct answer here is false. But now we want to take a look at the next one. Just want to erase all that first. So the next one wants to know if angle PTS, so we have angle PTS right here, and angle SRP, see angle SRP, do you see how they're connecting at S and at P? So the answer to that would be true. They are supplementary because they are opposite angles. I would like for you to try these 3 problems on your own. Hit pause, try them out by yourself, and in just a moment I will flip through and show you the correct answer.